Hello everybody, and welcome again to Science Live from the Creation Museum. We are coming to you on a beautiful sunny day here in Petersburg, Kentucky. We've got a little bit of wind outside, a little breeze on the pond, but it's a beautiful day. I'm joined again by Professor Danny Faulkner. He's our staff astrophysicist, so anything astronomy and physics related, we pull him in to make him explain all of those concepts. And a little tease for what we hope to do next week. Next Tuesday, the plan is, if all goes well, I'm trying to develop some little rockets we can build, and you can help us understand all of the forces that are involved there.
Very good.
So we had some questions about rockets and how rockets function when we did our physics of flight episode and talking about some of those things that we answered a little bit. But now we'll have a chance to actually do that. And anytime I get a chance to light stuff on fire,
I'm in too.
I'm all there.
Well, it's just the little kids in us, I think.
I think it is. Yeah. I'm still really
you like fires too, don't you?
Fourth grade boy who wants to just figure out how to do stuff and make stuff blow up and understand all these things. And so just love to explore God's world and understand all about Him through what is created. And that's really our goal. So I'll be monitoring comments today as Dr. Faulkner is teaching us and helping us understand all of these things. So if you've got questions about what we're talking about today, we're glad to receive those. And then I'll try to get back anything we can't get to on the show. I'll get back and answer on the Facebook page later. All right, so our topic today is all about optical length and lenses and creating images and all of those different aspects. And just a warning, kids, there's going to be some math involved later.
Four-letter word.
So buckle up and get ready for some math later. All right, so why don't you go ahead and get started.
Okay. First of all, what is a lens? It's a thing made out of a transparent substance, usually glass.
Usually glass.
Doesn't have to always be. Mm-hmm. It's very important to know it has curved surfaces.
Okay.
If you have flat surfaces on it, like a pane of a window, you don't get any images. Because how this works is when light travels from one medium to another, like air to glass, it bends or refracts.
Okay.
Mm-hmm. It bends or refracts a certain way depending on the physics we won't go into today.
Yes, and that's different than reflecting. Reflecting means it bounces off. Refracting means it bends.
Bends, passes through and bends as it does it. Mm-hmm. It's because of the different substances involved, different densities and speeds of light involved. And the important thing of a lens is that it's curved, because you see if it's just flat, it comes in, it bends one way, and then it comes out, it bends the other way, and you don't get any net effect. Mm-hmm. So you need these curved surfaces. So we'll be working today with this optical bench. This is this device right here in front of me. And in the middle here, we have a lens. In fact, I'll tell you, it's a double convex lens, which means you've got two convex surfaces like this, like a classic lens sort of shape. So it's going to bend really nicely. Back here, we have a screen for forming images. And out on the front end over here, on your left, my right, there is a light source. In fact, I'll just turn it on. You can see the light shining now, hopefully. And in front of that light, there's what we call an object. And it's a circle with a number 1 standing up inside of it. And notice it's right side up. That's very important. That's what our object is. And so we put the lens here between the object and the screen. And there are going to be two important concepts here we want to talk about. One is the object distance, that is how far the object is from the lens, or the lens is from the object. And right now we have it set up for what, 15 centimeters, is it?
Yes. Okay, so if let me grab the pointer over here.
Okay.
You can see the little red line on this, where our object is lined up with the 2 centimeter mark. And over here, if we follow down the scale, where the lens is at the 17 centimeter mark. So if I take the difference of 17 and 2, our length is 15 centimeters.
I'm going to write that down. I'm going to have an equation here we're going to talk about.
Okay.
D1. Write it down for D1.
D1, we're going to call 15 centimeters.
Right.
So I'm going to make a note here.
And I'll explain that in a minute here, what we're doing.
All right.
All right.
Noted.
Now, that's the object distance. Again, how far the object is from the lens. Now, the image is going to form over here on the screen. And that distance we're going to call the image distance. Now, if you bring the camera around so you can see the image, it's all blurry. It's a big blob of light there on the screen. What I'm going to do is I'm going to move the screen backwards a bit. And as it does, it's going to get a little smaller. And all of a sudden, you're going to see that number 1 showing up right there, pretty sharp. If I go too far out, it starts getting blurry again. Notice it's getting larger the farther out I go, but don't want to go for maximum size, you want to go for maximum sharpness. So I bring it back in, and somewhere along here, it seems to be the sharpest. All right, real sharp image. And what do you notice about it, Mr. Patterson?
If we come in here, and again, we're going to take the distance from the lens to the object. So we're at 17 here, and I come down the rail and I look carefully here, and I'm going to try and read this as carefully as I can. I'm going to line up this red line with the line on the scale here, and I'm going to call that 47.3 centimeters.
47.3.
But the total isn't 47.3 because I'm 17 on the lens and I'm 47.3 here. So I would find the difference of that by subtraction, and I get 30.3. I did that out of my head. He had to grab his calculator. Now, come on, kids, help me out here.
Yes.
All right, 30.3.
All right. That's what we call the image distance. D1 and D2 are those two things. Now, one other thing I want to notice about this image, though, what do you notice that's odd about it?
What else do you notice there, kids? So take a look at that image. Remember the number 1 that we saw on the black plate that's projecting the image is over here. So compare this number 1 to the one that's here on the screen. What do you notice about the image compared to the object? And the answer is?
Well, number 1, it's inverted. It's upside down.
Okay.
Most lenses do that. Some lenses don't, depends on what you're doing with them, what kind of lenses you have. But most optical systems will produce inverted images. Now, you can re-invert that. There's a way to do that, several ways to do that. The other thing, more subtle, I might want to mention is the fact that this image is larger than the object.
And that's another difference.
So we've magnified the image and made it larger. Now, there's another property about the lens we haven't talked about yet. In fact, the main property, and that's what we call focal length. And that's indicated by the letter F right here. And the focal length is defined to be how far behind the lens light from a very distant object will focus, like the moon or the sun or something like this. Now, on the optical bench, we can't do that because it's only about 1 meter long. We need something a lot longer than that. But thankfully, there's a nice little relationship between the focal length and the object distance and the image distance. 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. Now that equation is kind of intimidating to a lot of people. So we can manipulate that. What we want to find is F.
Everybody hates doing calculations with fractions.
That's right.
Hard.
I don't mind fractions, but most people don't like them. But F, if I rearrange this algebraically, for people taking algebra, you can check that in my math here to see. The focal length F then is simply going to be 1 divided by the 1 over the object distance and 1 over the image distance added together. So,
so we've got the values.
You did the calculation already?
We've got here. I did not do the calculation yet.
Oh, okay. You're waiting for me to do that?
I wasn't going to try that one in my head.
All right. That's a hard one to do. So we got 30.3.
Okay.
I got my trusty HP here. I can do this really quickly.
Value for D2.
Right.
And 15 is the value for 1.
Right.
So 1 over D2. Got a value?
I already did the whole thing.
Oh, you did the whole thing.
Yeah.
Okay, so he's already done it. And our value for the F, the focal length, comes out to
10 centimeters.
10.0?
Yep.
Okay.
So if we were to focus on a distant object such as the sun, and you know, all of us have done this at some point, you take a piece of paper or a twig or something or leaves and you go out and you focus on it. You have to put it 10 centimeters, which is what, about 4 inches?
Yeah.
Something like that.
2.5.
So that should be the focal length now, if I did the math right. Let me check my math a second time just to make sure I did it right.
Okay.
It never hurts to do it.
Always a good idea. We always, when we're taking measurements scientifically, I always pause and take a second measurement. I say, okay, it was 14.2, then I go back. I reset myself, I realign, take it again, just to make sure I'm getting things as accurate as possible.
I get 10 again.
All right, so 10 is our value.
Now, you know, in science, we've discussed this before, you don't just measure something once and you quit.
Absolutely. We want to take multiple values, multiple data sets to be able to analyze them and look at them together.
So our distance over here, our object distance was, we said 15, was it?
Yeah, we're at 15.
Well, we'll go to 20.
Okay.
So you need to move this. I can't see that side. So you need to move.
We're going to bring this over to
22.
22. So I'm going to line up my little red line there as well as I can with 22. Okay.
All right. So you can write that down again for the
That'll
first
be our
value.
D1.
And I'll turn the light back on. And if you look at the if you look at the image, it's not really focused, is it? And I can try moving it out a little bit, but it gets blurrier. So let's try moving it in, and as I move it in, it gets sharper, and it gets blurrier again. So let's try to find the sharpest part of that, and it's going to be about right there.
Okay.
So,
I want to give a shout out to the herb kids. They recognized the image was upside down, so good for them. Several people did, but nobody noticed that it was larger, which might be a little bit difficult to see on the camera.
Because you can have different distances the camera is away. So, okay, kids, take a look at this now. Pull back in again. What do you notice? Again, it's inverted, but what do you notice about the size? Larger or smaller than it was before? Getting any votes from anybody yet?
We've got enough of a lag. It'll take a few minutes to do that.
Well, to me, it looks smaller. Does it look smaller to you too?
It does.
It does, okay.
If anything, it's just a tiny bit smaller, not much.
All right, so it is a little smaller. And what about the image distance? What is that? I can't read it again. I'm on the wrong side.
So if we have
22 here?
of 22 on this one.
All right.
And over here, I'm going to line up those lines as carefully as I can, the red line with the white line below it. And I'm going to say that is 42.6.
Well, that's too easy, isn't it? 42.6?
Uh-huh.
So the difference from 22 is 20.6.
So 20.6 is going to be the value for my D2 this time.
Right. So
now we haven't changed the lens. It's still the same lens.
That's right. And we have it, all we changed is the object distance, and when you change the object distance, it has to change the image distance. Now, when we did this before, we got 10.
So let's have the kids make a prediction about what they think. Dr. Faulkner's going to calculate the focal length for this lens. Remember, the lens hasn't changed. What do you think the calculation has come out? He's going to use the same formula we did before, but the different values that we have. Go ahead and make your prediction, and he's going to do the calculation.
All right, I'll work on the calculation.
So our
we had
D1 value
22 and
was
20.6. All right. And I get 10.6.
10.6.
Yep.
Okay.
So if we were going to average just those two, we would call it 10.3, wouldn't we?
Yep.
Let's do it one more time. Let's do it one more time. Just what do you want to do now? 20.
Let's go out to
centimeters?
25.
All right.
So I'm going to line up my object distance with 25. So 25 minus 22.
25 minus 2 is 23.
20. Oh, that's why we got this wrong. We didn't take off our 2.
We didn't?
Or where did we put it before?
Oh, we didn't take it off. I need to change that then. That's 20 and 20.6. Okay. 20. All right.
Now, the fact that we came up with 10.6 probably should have clued us in. There was
20,
something messed up there. 20 and 20.6.
20.6. Very good. We make mistakes here,
Wait, no.
folks.
Okay. Yeah, that's
and
right.
I get 10.15.
All right. Okay. So I was surprised that it was 10.6
that large. That's not so large. That's just down to 15, 1.5 millimeters.
Okay, so
which is like that much. It's pretty small.
This is why we always double check our calculations. We retest, we redo measurements. If we would have done this again at those same measurements, we would have seen we had a bad data point, and we could have thrown that out in our calculations.
So we need to set this one to 27, don't we?
So let's set this to 27.
And that'll give us an object distance.
That gives us an object distance of 25.
I wonder if any kids caught us in that mistake.
I don't know. I'll have to check in the comments.
Kids, you better pay attention. We do get something wrong here sometimes.
Okay, he's going to adjust the object distance.
The image distance.
Image distance.
Get a focus. I think it's best about right there. You notice it's getting smaller. Smaller and smaller. So as we increase the object distance, the image distance is getting less and less, you may notice. We'll look at that table in just a minute here. But also the image gets smaller. What's the image distance now? We're at
27, and I'm going to read that at 43.8.
43.8, and we subtract 27 from that, and we get 16.8, I think. All right.
Okay.
And then I want to take 25 with that.
So again, make a prediction. It's the same lens. What do you think the focal length is going to be? And looking here at the comments, I see Ethan, who is 5. He said the image earlier was smaller.
Good.
And several people, Kristen and Wendy and others, everybody's thinking it's the same, that the image got smaller there. Okay, so with our calculation then, so if this is the same lens, we should think about the focal length being the same over all these tests. And what do we get?
10.05, which was really 10.0 if you put it to
If we go,
one place. And the other one above that should be, I think the first one was, the 10.1 was actually 10.052, I think, or 10.03 was.
Okay.
So they're all very, very, very close. They're within a millimeter or two of one another.
All right.
So you can see the numbers. These numbers change as we made the object distance increase. The image distance decreased.
Okay,
But
so
the
we would
focal
call
length-
that an inverse relationship.
Inverse relationship, which is what that one over stuff is all about.
Yep, so that's why the calculation uses 1 over, because it's an inverse function.
And then, but the focal length is the same.
Focal length is the
So we
same.
measured 3 times. We could take the average, and maybe it's going to be like 10.1.
Yeah.
And that's, again, that's 1 millimeter range there, which is very accurate, actually. If we did statistics on it, it would be really, really good.
And the little bit of difference there is probably because you're trying to judge with your eyeball loosely what the right focus is.
Yeah.
And the focus could be off a little bit each time you do it.
The first one, I didn't even use my glasses, which I ought to.
Oh, man.
That makes a difference. All right, you may ask, what good is this?
Sure.
And, if you use a camera, you have to focus it because the object distance changes.
Now, not a cell phone camera,
You're right, they
which
do it
does
automatically.
it digitally. We're talking about a camera, we call them SLR cameras or other things that have adjustable lenses.
Well, sometimes when I'm doing faint objects like astronomy things, I have to focus manually, but sometimes if it's daytime, I usually just use the autofocus on it.
Yeah.
But the thing is, you can watch the autofocus. It moves in, a little motor moves in and out, and that's changing the image distance, moving the lens in and out a little bit because the object distance is changing.
Yes.
You have to do that. Projectors, if you ever use those.
Yeah, so if you have a projector at home where you project a TV image or something up on the wall or at church, those types of things, if you move the projector back, the image gets larger, but what do you have to do to the lens?
You have to readjust it.
And usually you twist it, and there's a little screw head inside of there. The case has a screw on it, and as you screw it, it moves the lens in and out, which adjusts the distance between the object and the lens, and then that gives you the focus that we're looking for.
Now there are all sorts of optical devices that you can make. They have little magnifiers that work right side up. You get an erect image right side up as long as you're working within the focal length to do that. But what I really care about are telescopes.
Yes.
Here's my first telescope I ever
Let's
got.
go ahead and bring that right out here to the end of the table.
We'll leave the tripod in there. I'll just
Okay.
show the body of this. I got this telescope way back in 1967.
Wow, I was -8 at the time.
This telescope gave me my first view of Venus and its phases, the moon, and it gave me my first views of Jupiter and its satellites, 4 Galilean satellites, and then Saturn's rings, all way in the late 60s. I then graduated up to bigger telescopes from there. But this is what we call a refracting telescope. It's got a lens on the end, not very big. We measure the size of a telescope by the diameter of the lens. The bigger the lens, the more light it collects, and the brighter things appear in it. And so this 40 millimeter lens is not real big, as it turns out.
40 millimeters would be 4 centimeters, so about
1.4 inches, I believe, something like that.
About 1.5 inches.
Now, the lens is very long focus. It'll form an image way back around here someplace. Then we put another lens in here, actually a couple lenses put together, called an eyepiece. It's a small little eyepiece there, and the eyepiece magnifies what you're looking at through the image you're looking at. So this just forms an image like we did over there on the screen. It forms an image, except you don't need a screen to form an image. An image will form in empty space, really.
Yeah. If this image was here on this plate, whether I had the plate here or not, if I would put my hand here or a piece of paper
Or an eyepiece.
or an eyepiece, I could see it.
And that magnifier or eyepiece will make the thing appear larger. And this has a fixed eyepiece on it, but it turns out the eyepiece has a focal length too.
Yes.
And this is called the objective lens. It has a focal length as well. And you divide the focal length of the objective by the focal length of the eyepiece to get magnification.
Yeah. And the distance there and all of those pieces have to be balanced between the objective lens and the eyepiece. You can't just grab an eyepiece off of any telescope and slap it onto another. You're
Actually, you could. It's not a problem in most cases. This case you can't.
If
It's
you have
fixed.
enough adjustment in this.
If you have enough, usually that's the case. And I'll get to that in just a minute, how we change magnifications on telescopes. But it's important then when you pick your focal lengths, you want the objective to be kind of long and you want this to be kind of small. Why is that? Well, you want to take a big number and divide it by a small number to get a high magnification. And so if you took a small number for your objective and a big number for your eyepiece, it's going to demagnify. Folks, kids, have you ever done this? You could take your parents' binoculars. I remember when I had an aunt had a pair of binoculars when I was about 7 or 8, and we looked through the binoculars for a few minutes. Then we turned it around, and that was much more fun. Looking at everything was smaller.
Small and
if you look through the wrong end of a telescope, everything will look really, really tiny. This one magnifies about 25 to 50 times, depending on how you adjust it. Well, things are very, very, very tiny. Binoculars, it's only knocked down by 1/7 because it's low magnification.
Yeah, usually less than 10 magnification on binoculars.
Now, that's called a refracting telescope because it uses a lens that bends or refracts the light to form the image. This is a reflecting telescope. There's a mirror down here at the bottom. Think of a makeup mirror that your mom might have. In fact, let's get the cameraman looking down this thing. You can look down and can you see the mirror down there? And you might see a little dark circle in the middle. That's the secondary mirror, a mirror right up here near the top. And the makeup mirror is like this, except that, well, this is a little better optical quality than your makeup mirror that you have at home. Much better optical quality. But you could make a crude telescope out of that. So the light comes back up here, hits a very small flat mirror called a secondary mirror, and it sends the light then out to this little hole right here. And I'll get the camera to look down that hole, and you should see an image of the mirror. Now, Mr. Patterson, you get over, step over in front of it, and see if they can see you. Can you see Mr. Patterson over there?
Bring the light over here a little bit. We can probably.
Can you see him? Move around.
There we go.
Okay, not terribly in focus because we're not in the right position. That's okay.
Getting that camera to look through the eyepiece is a trick.
Now, the focal point is going to be up here near this hole, and I have here a little eyepiece right here. And you'll notice on the side, I believe it says 12.4 millimeters. Is that right, kids? I don't have my glasses on. That tells you the focal length of this eyepiece. Now, this is a neat telescope. Unlike this small telescope I had here, it has a fixed eyepiece. This one has different eyepieces. You just slide one in, and you lock it down, and away you go. Now, the side of the telescope here, I believe, says the focal length is 450. That's what that 450 means. That means the focal length is 450 millimeters.
So a model number on a telescope will often reflect that.
Oftentimes reflect that. I like that. Reflects it. Because
optical puns.
Anyway, 450 millimeters. Kids, the focal length of the telescope, the objective, the mirror, is 450 millimeters. The eyepiece is 12.4. Can you figure out what the magnification is going to be? I'll do it on my calculator. You can do it in your head if you want.
While you're doing that, we did have several of the people, Bridget and Kristen and several others, guessed the 10 value correctly. So anticipating that the focal length would be the same. So they're picking up on those things that if we've got the same lens, it's going to have the same focal length in different situations. Okay, so here we're calculating magnification based on the focal length of the objective and the focal length of the eyepiece. So what do we get?
Kids, I get 36.3, which will generally round off to 36 because there are little errors involved in these things. That's not huge, it's not tremendous, but sometimes you want a low magnification. When I'm looking at the moon, showing people the moon through one of the telescopes we use here, I start out at 50 because you can get the entire moon in it that way. If I go to higher magnification, you only see part of the moon.
And then you don't really realize what you're looking at if you're looking at an object that's close. But if you were to do something that's much further away, say Saturn.
It's very small. You want to boost that, so I go to higher magnification for that one. And magnification is not all it's chalked up to be. With a telescope, they'll generally say, well, this has a 200 power telescope. No, the telescope doesn't magnify. It's the eyepiece. And you can buy additional eyepieces and change those magnifications at will. Magnification is really oversold many times. There is a limit, generally caused by the quality of the optics, but on top of that, the atmosphere is very turbulent. And generally, if you use about 40 magnification for each inch of objective size, that's probably the limit.
Otherwise, things start getting blurry and you can't focus.
If you ever taken a photograph and had it blown up to make it big,
Yes.
It's very disappointing. I get really annoyed on TV shows. They'll have this little photograph and then they'll blow up this huge poster and it's really sharp. I'm saying, folks, it doesn't work that way.
Or they'll
That's
zoom
Hollywood.
in on the license plate that's 300 yards down the road,
And they
can
zoom
read
in.
the sticker on the all those things are kind of made up. Computers can help enhance those things. In computer, we call that pixelation,
Right.
when those things get expanded.
But the thing is, the magnification, when you go high, people are disappointed many times. I'll yank the magnification way up on the moon, let's say,
Yeah.
and people say, well, it doesn't look as good. It's bigger, but it doesn't look as sharp. You want,
Yeah.
you want to hit the maximum and then kind of quit at that point.
Absolutely. So the other day when we were talking about microscopes, I told people it's not a good idea to buy those little $50 kits because you're going to wind up with fuzzy images and things aren't going to look sharp and clear, and it almost gets more frustrating to try to look through it and everything's kind of blah. So when we think about telescopes, would you recommend the same thing with telescopes?
Yes, absolutely. You know, back when I was 50 years ago, you could go to a department store and buy a decent little telescope. You can't anymore. They're really pretty cheap. One thing that people don't know about is the mounts are really pretty unsteady, and that's very important. You really can't get a good telescope for much under $200.
Yeah.
And even if you can spend that in some department stores, but
Not get a good one.
Not get a good one. And so I suggest they search online. May I mention a particular product website?
Sure, why not?
Because people ask me where should I go, and I
Absolutely.
usually send them to Orion Telescope or just telescope.com. But it's the same place, Orion Telescopes or telescope.com. I have purchased several things from them and been very pleased. They have good quality merchandise at good prices. There are different types of telescopes. But entry level is going to be a couple $100 these days. But again, they have good stuff there.
All right, so we did have one question that came in that I wanted to ask, and I've got to find it here. It was, well, you guys are making too many comments. Talking about an eye doctor, do we have, using the lenses that an eye doctor uses, looking at lens 1 or lens 2, is lens 3 or lens 4? Is that the same basic idea that we're talking about here?
It's a little more complicated than that because they're not only looking for can your eyes, where they focus, but I think they also have to look at the shape of your lens, things called astigmatism, those kind of problems. I don't know how that's diagnosed, but that is basically what they're doing many times. They're having you look at different lenses, changing the amount of magnification you have there and seeing where you fit.
Yeah, because our eyes, especially as we age and other things, the lens is less elastic and you can't compensate. The shape of people's eyes are different. I talk about this in one of my workshops dealing with light and things that we do here. So we've got to be able to adjust the lens to make all those things.
I'm a victim of that. I've always had excellent vision. I still have excellent vision. It's just at my age, I can't focus within 2.5 feet of my face.
Yes, and that's why we carry these handy things in our pockets.
If I have to see something within 2.5 feet, I need that. If I want to see it sharply, beyond that, it's great. And my night vision is fantastic, which is, to me as an astronomer, is really important. I don't need glasses at night, and I hope I never do.
That's great. All right, so we hope you've understood a little bit about this. Now, we know you're probably not going to be crunching out these math formulas at home, but they're not really all that complicated. If you had a meter stick or even a tape measure, you could try some of these things with a little hand lens and a small light projecting an image.
And just a piece of paper.
Just a piece of cardboard or paper over here to form your image. So things that you could do to measure these things out at home. We are going to continue to bring these programs. Just as a brief heads up, we are going to be making some programming changes that will be announced in the future, so watch out for those things. But we just want you to be aware that that's coming. We're going to continue at least through next week bringing these things to you daily. And just a reminder, we've got our other programs happening today, so we'll be bringing you other programs at noon, 3 and 7. Hope you'll tune into those. And until tomorrow, have a blessed day and get out and explore God's amazing creation.